Hi, good morning, everyone. Thank you for the invitation and for this nice introduction. So today, I'm going to share with you basically only one project from all the projects that I could talk about in the area of human behavior modeling from data. Before I actually give you the choice of which project, because I have two, I just wanted to give you a quick overview of my background just to contextualize the projects. So as Kim said, my interest has always been on how to make computers understand humans as a necessary step to build intelligent systems that actually help us. And I started my work in the mid-90s at MIT, and there I worked mainly with cameras, initially with cameras. This is a picture of one of the first real-time facial expression recognition systems back in '96. Then I worked on machine learning models for recognizing human interactions, also using cameras. But at the same time, I was in the same team that developed the first wearable computers. So I did some projects on wearable computers and smart clothes, and we organized the first smart clothes fashion show in the world in '97 at MIT. Then in 2000, I moved to Microsoft Research, and I continued my interest in building systems that are interactive systems that recognize human behavior, but I expanded to more sensors. So this is a picture of a system that I did to recognize office activities in real time. Before going to Microsoft, I also worked on cars. So I built a smart car that could predict the most likely maneuver that the driver would do next using a lot of sensors from the car. And I also learned how to pilot Formula Dodge cars, which was really exciting. But the most relevant element for this talk is my work since 2004, 2005, when I realized that the most personal computer was actually the mobile phone. And if my dream was to build computers that would understand us, the best platform to do that was going to be the phone, because the phone is always with us, more than anyone actually, or any other thing in our life. So I did some early work on wearables before there were wearables, so I had to build my own hardware. This was back at Microsoft. Then at the end of 2007, I moved to Telefonica, and I created a research team there in Barcelona, and we almost exclusively worked on mobile phones, both modeling individual behavior and aggregate behavior. And now since January, I am at Vodafone, and we're also working on modeling human behavior with mobile phone data. So the underlying theme is modeling human behavior or human traits from a variety of different data types, from cameras and microphones and car sensors and physiological sensors to mobile network data. So if we look at mobile network data, there are a lot of different things that you can do with mobile data, and I don't have time to explain an example of each of them today. So I'm going to give you a choice. So if we have people, and the people are generating the data, if we model the individuals, we model people individually, we can have the next generation of business intelligence. Like as Kim mentioned, we could infer, for example, our personality from how we're using our phone. We could design new services. For example, we did a few years ago a project on inferring your credit score from how you use your mobile phone, and this is very valuable in developing economies where there is about more than 2 billion people in the world don't have a bank account, but they have a mobile phone, so we could use their mobile behavior to assess their credit worthiness. We can improve customer service, analyzing not only the mobile data, but also the customer call center data and voice data. Obviously, we can personalize the services and build recommendations, or we can come up with new things that haven't been done before. And then the other very powerful element is that we not only can model people individually, so we can see the phone as a sensor of humanity. And when we analyze the data in aggregate form, we can, for the first time in human history, quantify the behavior of an entire city or an entire country, or the planet. So this aggregate modeling, you can do a lot of services related to smart cities, which are part of the reality today in terms of transportation, for example, modeling. But there is a new area that maybe is less known to you, which we call big data for social good. And this is related to this nonprofit where I'm also collaborating, Data Pop Alliance. And the idea is, how can we use this large-scale data to help us make better decisions For example, in the case of a natural disaster, like right now is actually, unfortunately, there are a few natural disasters that have happened, or in the case of a pandemic risk. So, because I don't have time to give you examples of all those different projects, I'm gonna give you a choice, and the choices are the following. I chose one project on individual modeling and one project on aggregate modeling, and I'm gonna ask you to raise your hands and then you tell me which one you like better. The project on individual modeling that I thought of sharing with you is a project that we did a couple of years ago when I was at Telefonica, and it's a project on predicting, making an artificial intelligence system that would automatically detect if you are bored or not when you're using your phone. So it's a boredom detection algorithm, and we actually won Best Paper Award at UBCOM in 2015, and actually next week we are presenting the next version of this project at UBCOM this year, and it has also been selected for like a special discussion. The other project that I could talk about is in the aggregate modeling in the area of big data for social good, and it's a project that we did where we use large-scale aggregate mobile data and census data to automatically detect crime hotspots in the metropolitan area of London. So the challenge is, can I predict which neighborhoods are going to be a crime hotspot or not using data that is coming from the mobile network infrastructure combined with census data. And this is a project that falls within this area. So who is interested in the Boredom project? Raise your hand. Okay, so you do the count, Kim. I don't know, maybe it's like a third of the people. Okay. All right, so maybe, I don't know, a third of the people, I would say, or a quarter of the people. Who is interested in the crime project? More people, right? Okay, so let's go for crime. So bye-bye, Boredom. Have the Boredom first, so you can read the paper. It's very clear, everything. Sorry, I don't have the time to like.
Is the paper available though?
Here are the papers. So here are all the related papers. They are all available if you search online. If you search, so we have two papers on Boredom. I'm not going to explain the projects, but this is actually could be interesting to you guys. So the first paper, which was the UBCOM 2015 Best Paper Award, is about detecting boredom on the phone using mobile phone sensors. And then we did another piece of work that we also presented at UBCOM to infer what is called boredom proneness. So boredom proneness, so this is the emotional state of boredom, which changes constantly. And this is a characteristic, a trait. So we all have a boredom proneness in the same way as we all have a personality. And the boredom proneness is less known than personality, but actually boredom proneness is correlated with your probability, for example, to be addicted to gambling, or your interest in like new things and so forth. So it's an interesting trait to know, and we found that we can also infer boredom proneness from the patterns of usage of the phone. And then the new paper that we are presenting in 10 days is an extension of this one, and this one, I will make it available on my website. It's not available yet because it hasn't been presented yet in the conference, but if you are interested, I can also send it to you per email. So let's go now to the second project. So the main fact that is important for the second project is the fact highlighted at the bottom. The fact that not only the mobile phone is the technological device with the highest penetration in human history, but it's a global phenomenon that is happening both in developing economies and in developed economies. So with this observation, one question that I've been working on for the past 8 years, first when I was at Telefonica and now that I'm at Vodafone and at Data Pop Alliance, is how can we use the phones to help the world, to really help the world? How can we use the fact that everyone has a phone to help us improve the world? And that sounds like a very abstract question, so I'll try to ground it. So in fact, we are not the only ones working on this. There is a lot of other groups that have been working on this. And in 2013, MIT Technology Review declared this idea of using the data captured by mobile phones, not by smartphones, but by the mobile phone network infrastructure as one of the breakthrough technologies of 2013. And as many of you probably know, not just mobile phone data, also social media data and any other kind of human behavioral data has contributed to the birth, in quotes, of a new discipline called computational social sciences, which is the intersection between social sciences and computer science. Because for the first time, as I mentioned, we can actually model and validate a lot of social science theories quantitatively because we have access to all this data. So another important thing that has happened that I'm not sure to which degree is known is not in the computer science field, it's in the development field. So at the end of 2015, the goals for the world were ending, the goals that the United Nations had established, and they had to set new goals, which are the goals that we have now. And when we were thinking about which new goals to set, they realized that there was this thing called big data, and that data could be useful to the world, to improve the world, and to achieve these goals. So Secretary General commissioned a special report to a group of experts, and one of them was Sandy Pentland, my PhD advisor. This is publicly available. It's called A World That Counts. And they started thinking about how United Nations could include this concept of using big data to help achieve new goals and improve the world, and they called for a big data revolution. So in 2016, they defined the 17 Sustainable Development Goals, which I assume you've heard of. If not, these are the 17 Sustainable Development Goals. And there is a lot of work ongoing since, I would say, the very beginning of 2016 on seeing how we can use data to, A, measure the goals, because one of the criticisms that United Nations has had when defining all these goals is actually measuring the goals. The first goal is no poverty. But then the question is, how do you know if you achieve the goal? You need to be able to measure poverty. So how do you actually measure poverty? It is very difficult to measure the real world, right? So thanks to the existence of technology and data, we can do a better job. But the other question is, how can we leverage the fact that there is all this data to reduce poverty? Is there any way that we can use it not just to measure, but also to help achieve the goals? So in that context, as I said, for the past 8 years or so, I started working on this topic of big data for social good, and these are the 4 areas where I have experience, and these are all reflective of projects from my time at Telefonica. The first one, which I'm not going to explain, is public health. So how is mobile data useful for public health? In particular, for pandemics. So a pandemic is an infectious disease that affects a very large number of the population. And for an infectious disease to become a pandemic, people have to move. If I have the flu and I stay put in my house, I don't spread it, and probably it's not going to be a pandemic. But if I have the flu and I come here and I shake all your hands, and then you go to your homes and then you shake hands, then it becomes a pandemic. So understanding mobility and measuring mobility is very important. And because of the large penetration of mobile phones, we can actually quantify large-scale human mobility. And that's where we can contribute a lot for public health. And there's a publicly available talk on how we use that data in the context of the H1N1 flu pandemic in Mexico. Another very interesting area is socioeconomic development. So we found, not just also other research groups, that aggregate patterns of usage of the mobile phones are actually correlated with socioeconomic development and socioeconomic status. And measuring socioeconomic status is very important in developing economies because in many cases it's a proxy of access to education, access to sanitation, access to healthcare. So understanding how is the economic development of a region is very important, and we can do that by mining the aggregate mobile data. The most obvious probably area is natural disasters. So when there is a natural disaster, 2 important questions that you want to answer is how many people have been affected by the disaster and where are those people? And we can again infer population count from the levels of activity in the cell towers that enable us to assess the damage in certain areas. This is an example of a project that we did with the United Nations and the government of Mexico and the Polytechnic University of Madrid to see if the patterns of activity in the cell towers could indicate us the most affected areas by floodings. And this is in the case of Mexico. And we found that indeed we could use the cell towers as sensors of natural disasters. And then the project that I will explain to you now, which is on crime prediction. This is just to point that a lot of this work is also very aligned with this nonprofit called Data Pop Alliance. You can check online. It's been created by the MIT Media Lab, the Harvard Humanitarian Institute, the Overseas Development Institute here in London, and Flowminder, which is another nonprofit. So before I explain the project, I just wanted to show you a couple of quick videos. They're also from data from Telefonica on what kind of data I'm talking about. So this is like a 30-second primer on the type of data that I'm talking about. So as you all know, the mobile phones are connected to the mobile network, which has what is called BTS, base transceiver stations, which are the cell towers. And as an approximation, usually what we do is we do a Voronoi tessellation of the space in such a way that in the center of each of these cells, there will be a cell tower. And then all the phones that are in this area will be connected to this cell tower. All the phones that are in this area are connected to this cell tower, and so forth. So the spatial granularity of this type of data is not very good because it is at the cell tower level. And the density of cell towers is proportional to the density of population. So in urban areas where there is a lot of population, there are a lot of cell towers, and the size of this cell might be 100 meters by 100 meters, definitely not GPS accuracy. But then in rural areas where with low density of population, you might have a very big cell with maybe a few kilometers by a few kilometers. The other important thing to mention is that the data that the mobile network collects is event-driven data, which means if the phone is not being used, no data is being collected. So only when the phone makes a phone call or receives a phone call or sends an SMS or receives an SMS or is connected to the data network, there is some kind of an event. Otherwise, the network generally doesn't record anything about any of the phones. So the most commonly used data for development projects is called CDRs. Has anyone worked with CDRs before? No? All right. So CDRs means call detail records, and these are records that exist for billing purposes. You've all seen them on your phone bill, at least in the past. And what these records register is for every phone call that you make or receive, or for every SMS that you send or receive, there are a lot of fields, but for development purposes, for these types of projects, we usually use the timestamp, the encrypted originating number, encrypted destination number, the ID of the cell tower that this number was connected to. Only if this number belongs to the same mobile network operator, then we know the ID of the second tower, otherwise we don't know, and then the duration of the phone call. The rest of the fields, there are many more fields that are not really used for these types of projects. And then if it's an SMS, it's the same, but there is no duration, and obviously there is no content. It's just metadata about the events. But from this data, when you aggregate it in time and in space, so say for a few months and for a lot of people, then you can start computing three types of variables. Consumption variables, which measure the level of intensity of usage of the network, so how many phone calls, total duration of the phone calls, and so forth. Social network variables, because you can build what is called the call graph, which is the graph that connects the phones that are calling to whom, and then you can apply network theory algorithms to characterize that network and compute different network variables. And then you can compute some mobility variables at the cell tower level. So if you have over a certain amount of time, then you can have an estimation of flows of mobility. So I'm just going to illustrate it with two videos. This video shows the levels of activity in the cell towers in the state of Oaxaca, Mexico. This is from data from Telefonica. Before, during, and after an earthquake took place here. And coincidentally, not too far from here, last night there was another earthquake, but it was in the water, but now they are worried that there might be a tsunami. So I want you to notice what happens when the earthquake takes place. The epicenter is here. So if you can play the video, please. The size of these bubbles is proportional to the number of phone calls connected to each cell tower. So now the earthquake takes place and this big surge on activity. And the fact that there is this big surge on activity is very valuable because it enables us to infer how many people there were in the area affected by the earthquake. So when the government of Mexico or the Red Cross needs to send help, we can help in estimating how many people there might be in the affected area. When we add mobility, this is again Telefonica data, sample random sample of, I think it's like 1 million phones in the UK. So you get to see high level patterns of mobility. So if you play the video, please. So you get to see where are the main cities and where are the main roads. And again, this is very coarse data, very high level, very aggregated. But again, when you have no data and they say there is a risk of a pandemic, this is very valuable data because you get a sense of how are the flows of movement between different regions. So in this context, I will explain to you what we did for predicting crime. And this is joint work with Andrei Bogomolov, Bruno Lepri, Jacopo Stagliano, Fabio Pianesi, and Sandy Penland and actually also Emmanuel Letouze from Data Pop Alliance, the MIT Media Lab, and the Fondazione Bruno Kessler. So this is, I think, quite obvious. Crime has a negative impact in the quality of life of the places where it occurs. And there has been a lot of work on trying to find relationships between crime and different demographic variables, education levels, income, unemployment, and so forth. And something important is that there has been a lot of studies finding that crime is not homogeneously spread in space, but there are certain locations that concentrate crime, and those locations are called crime hotspots. And I'm sure that in whatever city you come from, you could tell me, Nuria, don't go to this neighborhood at night because it's not as safe as these other neighborhoods. And this is something that happens almost in every city in the world. When we look at the theories that have been proposed to try to explain crime and try to understand why crime takes place in different ways, I wanted to contrast two theories because that's what we did in this paper. So the first theory is the natural surveillance theory by Jane Jacobs. Does anyone know Jane Jacobs? Jane Jacobs was a very actually well-known activist and social activist from the US. And in the 60s, she actually wrote really nice books about what made cities livable. And she really thought a lot about how we could improve the quality of life in our cities. And one of the areas that she talked about was crime. And her theory was saying that you need cities to be very diverse and to be to have a lot of people coming in and out, because then there is this concept of natural surveillance. We all act as policemen of each other and we protect each other. So cities with a lot of diversity, a lot of movement of people should be safer than cities where there isn't such a movement, because then there wouldn't be this natural surveillance phenomenon. But about 10 years later, Newman proposed what seems the opposite theory, which is the defensible space theory, where he said, well, actually, a lot of diversity and a lot of movement leads to more anonymity, and when people don't really know each other, then there's more crime. So if you have sort of like a gated community where everyone knows each other, then it's easier to defend, because if there is a stranger, it's very easily detected because it doesn't belong to the community. So he was saying, well, you have a high mix of people, then there should be more crime. So the question in the air is like, who is right? Is Jane Jacobs right, or is Newman right? So before I tell you what we found, I want to ask you what you think. So who thinks Jane Jacobs was right? Who thinks that Jane Jacobs' idea of high diversity, high movement makes places safer is right? Okay, very few people. So who thinks Newman's theory of defensible space, is right? So a little bit more people. So I guess the rest have their own theory of crime. Maybe we can discuss it later. So we call it the IntelliSys theory.
Can it be possible that it depends on the crime?
It depends on the type of crime. So that's a very good question. I'm talking here about crime in general terms, and indeed, there are many different kinds of crime. There's violent crime, there's non-violent crime. In fact, most police crime databases have a taxonomy of crimes, and it's a very rich taxonomy. And we didn't get to that level of detail in this work, it is true. But I don't know right now if there is any empirical evidence on whether indeed the type of crime has a factor to play on which theory is right, because this is quite early work, and this is relatively new work. There isn't really a lot of related work on this topic yet. So this is a very interesting open question to explore. Does the type of crime play a role in determining which ones are the factors that make a place safer or not?
Will say yes.
Probably yes, but there is undergoing work through Data Pop Alliance in Colombia, and they're looking deeper into the types of crime, but I'm not going to have the time to explain it here. This I already explained, but it's important because when you talk about crime, most people think about Minority Report and predicting whether an individual is going to commit a crime, and predictive policing, a lot of it is about that, and this work has nothing to do with that. We are focusing on a place-centric perspective, so we're not looking into an individual, we're looking into a place, and we're trying to see if that place is going to be a crime hotspot or not. So the location is is London, and I'll explain you the data that we use. So this data was shared as part of a datathon for social good that Telefonica organized in 2013, where it was here organized together with the Campus Party in London, and they shared a number of data sets. It was in collaboration with the Open Data Institute, but for this project, we only used these 3 data sets, which I will explain next. So the first data set is a data set coming from the mobile network. They didn't share exactly the same as I explained before, but it's a variation on what I explained before. And it was data coming from a product called Smart Steps. So in that product, instead of doing a Voronoi tessellation, they do a grid. And then for every grid, and as you see, the size of the size of the square in the grid changes depending on the density of cell towers as well. So rural areas have big squares and urban areas have smaller squares. And then for each of these squares, what we had for each hour, we had an estimation of how many people are in this cell, so an estimation of how many people were in each cell, and this is coming from the levels of activity in the cell towers. The percentage of these people for whom that cell is their home, that cell is their work, or is neither their home nor their work, so they're visitors of the cell. And this is also coming from the mobile network. And then these two are coming from a market research company. The gender splits, so what percentage of these people are male versus female, and the age split, what percentage of people are in their 0 to 20, 20 to 30, and so forth. So this is the dynamics. We're going to call it the Smart Steps data set. It captures the dynamics of the place. Then we had the crime data. This was provided by the London police, and we only had 2 months. So we used 1 month for training and 1 month for testing. It was aggregated at a monthly basis. And then we had the geolocation of the crimes that occurred in the entire UK, but we only used the London metropolitan area. And we had to define the concept of a hotspot. So we computed the median number of crimes, and it was 5. And then we thought, okay, any place that has more than 5 crimes is a hotspot. Otherwise, it's not a hotspot. The spatial granularity is not this, which would be nice, is what is called the LLSOA, which is the census sector in the UK, which is these irregular areas that have a median population of 1,500. So for each of these LLSOAs, we had the aggregate number of crimes in the month, and then we defined whether they were a hotspot or not. And then we also had the census data, which are 68 very rich metrics about the population of each of these census sectors. So we had demographics, we had information about the households, the cost of the homes, employment levels. In the UK, there is even happiness levels, healthcare levels, life expectancy, and so forth. So this is what you would consider like a traditional kind of data set. It's very rich, but it's a one sample capture in time. Whereas this is not very rich, really, but you have it every hour. So the question that we wanted to understand is, what is the role of dynamics, versus semantics, in a sense, because this is a very rich description of the place. And what is more important in determining whether a place is a crime hotspot or not. So I'm just going to go quickly through the project because it's more complicated than this. It looks relatively simple when I explain it. But so basically, one of the problems that we had to solve was the geo-referentiation, because here we had these irregular shaped places, and here we have the cells, but it's relatively easy, like to do the matching and attribute, and put all of them in the same reference framework. And then this is very important. So the mobile data is a spatio-temporal data, and one of the open questions is, what is the right temporal granularity for the problem at hand? So for example, I said that we can compute, so we had the number of people in each cell every hour. But the question is every hour the right time granularity? Or is it aggregated every day? Or is it every week? Or is it morning, lunchtime, afternoon, evening? Or is it weekdays versus weekends? I mean, there are many different ways that you can aggregate the data temporally, and you don't really know a priori. So what we did was a brute force approach. We computed all possible time windows, and we computed all possible statistics on these variables over those time windows. So we ended up with over 6,000 variables, which obviously is too high of a dimensionality for the amount of data that we had. So then we applied a standard state-of-the-art feature selection algorithm to reduce the dimensionality to 68, the most discriminatory 68 features, to have the same number of features as the census data, because the census data has 68 features. And that way we could have 2 models of the same dimensionality, one that was capturing the dynamics in 68 features, and one that was capturing the demographic information in another 68 features. From a classification approach, so this is a classification problem. What we want is for every cell in space, we have as input either the Smart Steps data or the census data or both of them. And what we want is the algorithm to tell us if that particular place is going to be a crime hotspot or not in the next month. So this is a binary classification problem because it's like 0 or 1. Is it going to be a crime hotspot or not? We tried different state-of-the-art classifiers, and we got the best results with random forests, and we used tenfold cross-validation to train the model. And these are the results. So to me, the most surprising result was that the model that used the census data was performing worse than the model that used the smart steps data, even though the smart steps data had no semantics, really. It was just about the dynamics of the place. And then when we combine both types of data, we managed to improve a little bit the performance. But this was significantly better than this one. This is a visualization of the results. Is difficult, really, to see. This is the ground truth, and these are the predictions. And you can see that when it's roughly 70% of the time, it's roughly right. But what I think is the most interesting is not even the number, is the variables that the model considers to be important, because it sheds light on who was right, Jane Jacobs or Newman. So the first observation was that the daily features were the ones that the algorithm picked, as opposed to other time granularities. So it seems that the daily dynamics is important. And then we had two findings that support one of the theories, which I'll reveal next. So the first finding was that the higher the ratio of residents in a cell, the higher the crime. And this we interpreted as contradicting Newman's theories of the defensible space, because we found that the higher the number of residents in a place, the higher the crime was in that place. And then we also found, so we computed the entropy of a lot of the variables, and the algorithm in the feature selection process selected a lot of the entropy-based features. And we found that the higher the entropy, the lower the crime, which you could interpret as supporting Jane Jacobs' theories, because the entropy captures how predictable a variable is, which you could say, well, is similar to this diversity concept that Jane Jacobs had, and we were finding that the higher the entropy, the lower the probability of crime. Another interesting observation was that when we built a joint model that had both the dynamics features and the census features, and we did the feature selection, only 6 out of the 68 top features were actually coming from the census. So the remainder 62 features were coming from the dynamics. So it seems that the dynamics is much more important for this particular problem than the actual traditional census data. And to me, this is a little bit sad somehow, because the features that the model picked as the most predictive features from the census data were features that I think reinforce stereotypes on which areas have crime, because we're related to migrants, to overseas, to people that were born abroad, and so forth. So the main implications for this work is it's one of the first works that has looked into this completely different type of data as a valuable data source to help us understand safety in cities and crime in cities. And as I said, there is follow-up work happening now exploring deeper the theories of Jane Jacobs in the country of Colombia. If you are interested, not just in this paper, but in the area, there is a lot of papers available in the area of big data for social good. They're all publicly available, and also talks that you can look at. So with this, I finished my talk. I didn't have a time to talk about this, but not only I think that phones are a valuable, incredible tool to help us individually, but I really invite you all to think about the phones as a tool to help all of us collectively. And this is something that I never really thought about when I used a mobile phone for the first time, 15 years ago, and that, I find extremely inspiring right now. So thank you so much.